Welcome to Unchatted Waters. In this episode, we go on a journey across the sky and talk about how remote aircraft can provide data for science, from understanding changes in the shape of our coasts to monitoring habitats. We explore how this technology is evolving and how future potential uses could be sky high. Starting motors, taking off. Welcome to Unchatted Waters, the podcast that talks to the people behind the science. I'm Kirsty Bradley, your host, and I'm excited to introduce my two guests joining me on a journey of discovery in our new series. Tony Dolphin is a principal scientist in coastal geomorphology, which is the study of coasts and how they advance and retreat. He provides advice on monitoring changes and impacts of activities in coastal zones, both in the UK and across the world. Sara McIlwaine is a coastal processes scientist. Her work focuses on how innovation and technology used in our skies can help us monitor and understand how our coastlines change. Welcome to the podcast.
Hello.
Hello.
Great to have you. So let's kick off understanding what these remote aircraft are. Now, Sara, you're a pilot, aren't you? Can you tell us a bit about what that entails?
Yes, so I am a pilot, but not of traditional aircraft. I fly remotely piloted aircraft, or they're more commonly known as drones. Drones are very much the same as the normal aeroplanes that you'd use to go on holiday, but without pilots and much, much smaller. There are different types. There is a fixed-wing drone, which looks and operates like a very small aeroplane. There is a quadcopter, which operates very much the same as a traditional helicopter, and hybrids that do both. Both hobby and scientific drones can record photos and videos. However, scientific drones help us to answer real-world scientific questions, such as coastal erosion, and allow us to map habitats. The drones that I fly range from the size of a small water bottle all the way up to about a medium-sized suitcase. It's not about size though, it's about purpose. Scientific drones are great for precision, safety, and accessing risky environments.
So I'm going to ask you a follow-up question on that. What do you mean by precision?
By precision, I mean that surveys and flight plans can be repeated time and time again in multiple different conditions and potentially even locations, allowing us to get really comparable data.
So it's really a balance of a repeatable survey, but also resolution in that precision.
Yes, exactly that.
Great, thank you so much for clarifying that. So I'm going to come to you now, Tony. I don't really remember drones being around when I was a kid, and they've only really come into my awareness in the past maybe 5 years. So how long have they been around and how long have they been serving science?
Good questions. It's relatively new technology. The cool thing about drones is that they give us an aerial view of the land, the coast, the sea, even Mars. And from a scientific perspective, that allows us to study anything that you can see. And indeed some things that you can't see with human eyes. So I started off on this journey with drones when I had an interest in studying a rock platform that was eroding.
So what is a rock platform?
A part of the coast, an intertidal section of the coast with rock pools.
Oh, okay. Great.
And it was quite a complex setting that required a team on a ground survey about 2 weeks to survey at just one point in time, really detailed. And the problem with this platform was just the amount of time. It was really unfeasible for us to study it. So in 2013, drone technology was just emerging, and we figured out that we could do the same survey in a few hours.
Wow. Versus
weeks of staff time. So that was in 2013 when the drones were in their infancy. There were no hobby drones. Scientific drones were novel. We had our first drone, Alice, who was a fixed wing. Sara mentioned the fixed wings before. It was launched by a 10-metre long horizontal bungee cord to give it propulsion. It would enter a glide, the pilot would switch on the engine, and then we'd go and fly our survey. We didn't have a runway, so on the way back we would belly land, effectively a controlled crash landing on the grass. Today the drones are much safer, as Sara mentioned, and they're much easier to use. The key features for many scientific applications are the ability to survey wide areas, generally up to about 1 kilometre at high resolution. We typically survey at a ground sampling distance of 1 to 2 centimetres.
That's the jargon on there, the ground sampling distance. What does that actually mean?
Yeah, so commonly we talk about resolution. So it's essentially resolution, but more accurately, it's the distance between 2 pixels on the ground. Each pixel in the photo is 1 or 2 centimetres.
Right, okay.
So that's an important point about resolution, and where the drones are quite special, you can see a lot of things that you can't see in satellite images or traditional aerial photography because the resolution's not that great.
Is that the minimum you can get to, like 1 to 2 centimetres, or is it kind of dictated by height?
Exactly. It's largely controlled by the camera that you've got and also flying closer or further from the subject of interest. Ecological features, some seaweeds, we collect data at 1 or 2 millimetres.
Wow.
By flying about 5 to 10 metres above the surface instead of the normal flights, which are more like 100 metres.
Great. So Tony's talked a little bit about understanding rock platforms and other aspects like seaweed and ecological sites and understanding the environment. Why are drones so important for our coasts?
Drones have become a vital tool for understanding our coastlines. The reasons why are because they're fast, they're really cost effective, and we can access really hard to reach places such as fragile cliffs, low tide zones, and intertidal habitats. With drones, we can map these habitats without disturbing them, whereas people walking around just naturally has some impact to the environment.
Tony also mentioned with his example, he was able to do things in a shorter time period. Can you use a smaller team as well?
Yes, comparing a ground survey team, we would sometimes take 3 or 4 days with 5 or 6 people. With a drone team, we usually operate with about 3 people. So this data supports long-term coastal monitoring for coastal erosion, scientifically significant vegetation such as seagrass beds and driftline species.
What's a driftline, please?
Driftlines are a rare beach habitat. They're found on loose pebbles above the high tide line. They support tough, quite short-living plants, and they thrive despite the storms and salt water, which makes growing conditions quite challenging for other plants. It's a very fragile but vital ecosystem, and it's protected for its unique biodiversity and resilience.
So if I was walking along the beach, what would it look like?
Going to be honest, some quite small plants growing in the gravel.
And right at the front, they're kind of the seaward most plant species.
Right.
Not at the sea line, but they're before you get to the dunes. They're the hardiest
Right.
of species.
Okay, so I was thinking like the tide line where you maybe have seaweed that's left over from high or low tide. That's not what we're talking about. We're talking about the plants that are at the very edge of the dune that might get wet sometimes, might need to deal with quite changing environments. They're quite hardy and quite important. Is that right?
You're partially right though, because the drift line is I guess an area where there's more organic material that's been brought up into that higher environment during a big storm.
Right.
And so I think that's where the driftline term comes from, and that's before you get into the dune setting where the dune grasses are more of a forest of grasses that kind of self-support.
So now we've understood what driftlines are, let's go back to the seagrass that you were talking about. It's a really important habitat. It's quite fragile, you were saying. Why is it important?
So it's vital for 2 reasons, mostly because it stores carbon, and I believe there's a podcast previously about carbon. And it also provides a nursery ground for some species, such as seahorses. It's very important that we understand it. Because we can collect centimetre level resolution, which Tony's already explained, it means we're not just taking pretty pictures. We're collecting data that helps us to answer real scientific questions. We can identify how healthy it is, its location, its abundance, how it's changing throughout the year, so we can see if there's any seasonal variability. And since the drones are safe and repeatable, they're really perfect for long-term monitoring of our changing coastline.
Seagrass is really sensitive to water quality, and the seagrass is essentially an indicator of the health of a water body.
Thank you. So we've talked about habitat mapping, we've talked about an important habitat example, and we've also mentioned how the coast is changing. So why are things like coastal erosion important?
Well, this is my topic. So it's a fascinating place to work and understand, and almost everyone's drawn to the coast. It is a hazardous environment. It's always changing, and it exposes those who live or work or holiday near it, and also human infrastructure, roads, buildings, power stations, to risks like coastal flooding and erosion, which are natural phenomena but they are exacerbated by climate change-induced rising sea levels and, in some cases, increased storminess. Coastal systems are quite complex. One of the ways that geomorphologists understand them is simply by monitoring and measuring them and looking at how they respond to the input conditions, the day-to-day input conditions and those climate change input conditions. So the start point is to understand the physics and behaviours of the coast, and then to, perhaps with computer models, perhaps through observations over the last 20 or 30 years, looking at how they respond and building models to forecast how things might be on the coast in the future.
So then how do drones help you understand our coast?
Drones allow us to study the coast in a way that we haven't been able to before. And go back to the traditional way of measuring coastal change. It's using cross-sections of the beach placed at different locations along the coast. In your GCSE geography, you might have learned about that as beach profiles.
Can you describe what a beach profile is? Because it's a long time since I did my GCSEs.
Sure. So imagine you're standing on the beach at the top of the beach, and you're nice and high up, and you've got a pretty fancy GPS with you that tells you how high you are. As you walk down the beach and as you move along the beach, you're effectively tracing a profile, a cross-section. So as you go up over little hills and down all the way to the water's edge. That line on a graph that we look at, how it changes over time. And if it's a retreating coast, obviously it'll be going backwards. Growing coast, it will go forwards. And the features, the morphology of it, the shape of it will also change over time. Here in East Anglia, the regional monitoring scheme has the profiles every kilometre on the coast, which is amazing. It's a massive coast, and to have a measurement point every kilometre along the coast is really, really good. And this is a classic problem in environmental science. We can't measure everything everywhere.
All at once.
And so we do spend a lot of time designing how we're going to sample and where we're going to sample. The reason we do that is we want our samples to tell us about all of the areas around that we haven't measured. And there's uncertainty because we haven't measured in between. And that's the problem with the beach profiles. Even though they're 1 kilometre apart, are they telling us about what's happening in between that 1 kilometre? I've got a bit of scientific FOMO, fear of missing out, on what happens in between those profiles. And it turns out in East Anglia, often something different is happening. And that's where the drones really come into their own, because they're measuring within our area of interest, they're measuring everything at this glorious 1 to 2 centimetre resolution, so we can study the whole system.
It's like going from standard definition TV to 4K.
Is
that a good analogy?
Yeah, that's a really good analogy. And I mean, it's really quite remarkable that we can do it, and we can do it quite quickly. I had a list of cons. I mean, we've been talking about all the great things about drones. There's not many cons. But the main one is that you do generate a lot of data. Imagine our beach profile with a few points down to the water's edge and spacing of 1 kilometre. Now we've got every centimetre between those profiles. There's quite a bit of data to work with. The other limitation is more around safety and regulation, and a little bit about what kind of battery you've got on your drone. With the size drones that we use, a safety limitation from the Civil Aviation Authority.
That's the UK air law on how far away from the pilot you can fly, which is 500 metres. But that can be reduced if there's something that's obscuring your line of sight. So, for example, if you're flying around some trees or some buildings and the drone goes past them and you can't see them, you'll need to move so you always can see the drone in the air.
Great. So Tony started to introduce some of the practicalities with flying these drones. I want to come to you, Sara, now for your pilot's view. How do we take these drones to the skies for science?
So taking to the skies isn't just about launching a drone. It's a whole process. And most of that process happens before we even step foot on the beach. First of all, as a remote pilot, you need to have a license and you need to be accredited to fly commercially. Second, you need to have the correct permissions. So, as Tony mentioned, the Civil Aviation Authority will grant an organisation permission to fly. But there's also other more local permissions you might need, such as from Natural England or the local landowner or any other interested parties who have a duty of care for that particular area and maintaining it. Once you've got everything that you need to actually arrive at the beach, before every flight, we meticulously look at our flight plans, check the airspace restrictions, and sometimes even contact local airports or police to make sure that we've got clearance, to make sure we're not sharing the airspace with any other users. Once we've got that, we can start looking at our flight routes, our altitudes, and the timings of our survey. So we'll need to make sure we're timing with low tide if we're interested in the below high water area, the intertidal zone. It's not all just about the paperwork though, it's also about the people. We have scientists on our team of pilots from all areas. Some of them have been apprentices and have worked their way up, all the way up to our senior scientists. And it's a skill that really grows with your career. And then technology evolves, so does the role of remote pilot. We're seeing more automation, some better sensors are coming in, and even in AI integration. So flying for science isn't just about piloting and flying the drone, it's about unlocking new ways to understand our environment.
Okay, great. We're covering a lot of ground here on this flight and this journey of discovery. So I wanted to think about what we've covered so far. So we've talked about what a drone is, how we can map important things like habitat and ecological science to understand the environment, as well as physical aspects of science in terms of your coastal erosion and coastal changes. We've talked about the pros and a few cons on drones, and we've talked about how we actually conduct a flight and a survey. So let's imagine we've come to the end of our flight and we've landed our drone. What do we then do with that data? You said you've got thousands of images to go through. What do we then do with all of that information?
Yeah, that's right, Kirsty. There's literally thousands of photographs for each flight, and obviously if we've got a bigger section of coast, we might have 3 or 4 flights to do so. That can put us into the tens of thousands of pretty high resolution individual photographs, and we turn those into 2 core scientific products. The first is called an orthomosaic.
Jargon now, what's an orthomosaic?
So an orthomosaic, a photographic map. So all of those photos that we've taken, an important property that Sara will have built into the survey design is that they will have overlap, a really high degree of overlap, forwards, backwards, and out the sides. So there's overlapping areas everywhere, and within those overlapping areas there's literally tens of thousands of features in the photo. Might be a different coloured pebble or a plant. We can see those features from different angles, and that allows us to stitch them together and make this photo map. So those overlapping pairs can also be used to create a 3D map of the beach, that is topography or beach contours if you like. And over time we can study how those contours move and change. Interestingly, underneath them, that allows us to get to really the gold standard of beach health, if you like, which is the beach volume. How much sediment is there in the beach? A healthy beach has lots of sediment. A less healthy beach won't have as much, and by having those contours we can calculate the volume underneath and then look at how the volume is changing all the way across the beach again, not just at the beach profiles but everywhere. So if there's an erosion hotspot and maybe there's a property starting to look like it's at greater risk, we'll see that in drone data.
I imagine a drone is just looking straight down. So how do you get a 3D model with the drone that you mentioned earlier? If you've got the nice mosaic, I can really imagine that. It's like a jigsaw puzzle. You got all the overlap and then you kind of map it all out and look for those features and label them. But how do you then get a 3D model out of that?
Imagine the space that you're sitting in right now. You're probably seeing that space in 3D, and that allows you to judge distances, different distances between the objects that you can now see. And there are slight differences in how that's perceived from each of your eyes, and that allows us to get to the stereo vision. Now, the drone only has one eye, it's the camera, but it's very clever in that we can use the photo that's taken in one position, and then just a few seconds later, another photo is taken of the same image underneath, and between those 2 positions that allow the drone to have stereo vision in the same way that you would if you could fly and you're flying above the land. The method's called structure from motion, and from that we can reconstruct a 3-dimensional landscape from 2-dimensional photographs.
So that's given us a real new perspective of the eye in the sky. And we spoke previously at the beginning of the episode how technology has changed. Drones probably weren't around in the last 10 years. So how is new technology evolving even further? And what other tools can we attach to a drone?
Most people will think of a drone as a flying camera. In science, we think of them more as a flying sensor carrier. So there's the standard photo and video cameras. We use those plus many more sensors. We can use LiDAR.
What's LiDAR? Jargon alarm.
LiDAR uses lasers to measure elevation and surface structure, similar to bathymetric data, but for the land.
So like an echo sounder pings a sound to the seabed and bounces back and listens for the bounce back to understand the 3D features of the sea floor, LiDAR does the same, but with lasers. So it's listening back for the laser and then analysing that return.
Exactly that, yes. We then use thermal cameras to detect heat or multispectral sensors.
Another jargon alarm. What is a multispectral sensor?
So multispectral sensors go beyond the visible light that we can see with our human eyes. You might have seen this on a BBC documentary, probably with David Attenborough, looking at how insects view the world, and you can see plants and they look really funny colours on the TV screen. That's because they've used a multispectral sensor or multispectral camera. We're using those to help us identify plant species.
So would a certain plant species light up in a different way using this special technology?
Yes, we can identify individual plants that are growing in the vegetated driftlines that we were talking about earlier. Each plant has a unique fingerprint as such of wavelength. Wow. So even when they're tiny or hidden in other vegetation, these fingerprints of light are able to be detected, which gives us the ability to do species level mapping from the sky in a really short data collection period compared to if we were on the beach on our hands and knees with our guidebooks.
Looking at leaf shapes.
Identifying individual plants, yes. From that, once we've got that huge data set, the multispectral is essentially 10 individual cameras on one sensor. So that's 10 times that amount of data.
So is it looking at 10 different wavelengths of light?
Yes, exactly that. So data size is huge. So that's where we're bringing in AI to help us interpret this data. And we can train algorithms to help us spot litter that's washed up on the beach. It can also map habitats. In this example, it would be identifying where the plants are living. It can also detect changes in beach volume. It's a really powerful combination. Drones give us access to this perspective from the sky. The sensors give us the level of detail that we're interested in. And then AI helps us make sense of it all.
So it sounds like a really nice combination, like you said, of technology and really celebrates how technology is developing. So I want to come to you now, Tony, and think about the wider research and science as a whole. How much potential do drones have to serve science now and in the future?
It's really anything that can be seen. So, for example, looking at toxic algal blooms or oil spills, certainly chemical spills, pollution, those sorts of things are covered because they're surface features that you can see and detect and measure.
So what are you excited about as drone science develops further beyond the technology we currently know?
I think it's probably mainly around different sensors. Sara mentioned multispectral, so hyperspectral scanners, the ones that continuously measure all of the bands of light, already exist. It's very new and novel. It's something that we would like to be able to use, hopefully in the near future. I was going to say as well, there's kind of potential for automation and AI to do some things really, really differently. Imagine, for example, if we had the drone parked in a dock, different beaches around the coast, and it could be integrated. The drone could go up by itself, survey a section of coast, come back down, land in the dock, send that data back to the office. There would obviously be regulatory issues around that, a drone flying it by itself, but it's probably something that could be achieved.
Wow, so it's probably similar to some of the topics we've covered in other episodes to do with autonomous gliders and stuff. There could be autonomous drones that are developed in the future, considering all of the regulations and safety and everything. Who knows where technology will go? So I think this is a really nice place to end the episode here. Thank you so much for all the information. And it takes us to our feature. So for this new series, we are talking about treasures. Along this journey of discovery, we've found lots of pieces of treasure, and I wanted you to select one. So I think, Sara, I'll come to you first.
I don't know if this is a treasure found along the journey or treasure I'm hoping to find in the future. There's a new drone that can take off from dry land, fly in the air, and then land on the surface of the sea, and then effectively swim along the surface, snorkeling, and take photo and continuous video for that whole journey. It's really cool just in itself, but scientifically it would allow us to video and map really shallow waters where boats can't get to, and it might be dangerous perhaps for divers or snorkelers to do it themselves. I'd really love to find out more about that technology and get more involved in that integration of from land to sea, and then we can really understand those coastal regions and what's happening. Not treasure I found, but treasure I'm looking for in the future. So yeah, just need to find a map to get us there.
Thank you so much. And to you, Tony, for your piece of treasure.
Well, speaking of future treasure, drones are pretty common now. Lots of people have got them, and they've got the sensors on board, most of them, that we use for our science. Perhaps not the same quality, but they're still there. So I think another future treasure might be finding ways for citizen science, people who like flying drones for when they're going hiking and so on, to also be able to capture the right kind of data. Essentially, when you think of how many drones there are in the United Kingdom, imagine if a small percentage of those collected some of this kind of data, the amount of information we would gather and the amount of knowledge around the broader coast that we could draw upon would be really huge. And I think that would empower people as well. They'd be able to study their own coast that they might be interested in.
Do we know where drones came from? I'm just thinking back where we are going in the future, where we've come from. What was the first drone like? What did it look like before we started having these little helicopters?
So, Kirsty, the first drone was invented by Nikola Tesla in 1898. It didn't fly. It was a remote-controlled boat, but it's widely recognised as the ancestor to modern-day aerial drones.
Wow. And now we have things with 4 blades, quadcopters, whizzing around the sky, giving us an aerial view of the planet we live on. And I think that's really inspiring that we can have a different viewpoint and take a journey across the sky. So I want to thank you today for your time, and I've really enjoyed the flight.
Thanks for having us. It's been great to chat. Thank you.
Thank you.
Thank you for listening. This podcast was made by CFAS, the Centre for Environment, Fisheries and Aquaculture Science. To keep up to date with us, follow us on social media using @CEFASGovUK. We hope you can join us again next time.